So now we have our bitstream, and it's time to think about what we actually have right now. So we have a complete FPGA design containing two cores basically. One is the grayscale one. So what does is it takes the three channels of an RBG image, for example a JPEG image, and calculates a grayscale value for each of these pixels, so we get a grayscale image. The second core we have is our Sobel core, so this edge detection which works on grayscale images. So the next thing we now need to do, because there's no images in the hardware, we need to communicate with our accelerators and provide them data and tell them to execute on some image, for example. So we've put together a small cheat sheet of the TaPaSCo API for you. It's also on the ARC 2019 website in the TaPaSCo tutorial page. At the very bottom you'll find the cheat sheet that's just the 2 slides we show here. So for the C++ API, the very basic, or the all it starts from is this class TaPaSCo. And so what we need right now is 3 things. We need to put data into the FPGA memory, we need to get data out of the FPGA memory, and we need to tell our cores to start, to actually execute something. So starting a core in TaPaSCo Pollens is called launch. So there's 2 different launch commands, as you can see up here. One is taking this redval thing, so if your core is actually returning a return value, so if your HLS code is having a return something in the end, you will need this launch function. And if your kernel is only operating on the memory without giving a return value but writing the return to the memory, for example, you can use the version without the return value here. So the other things is the arc, so that's just template magic, variadic template here. So that's to launch a kernel. We still need to get our data in and out, and so the basic construct for that is wrapping a pointer for TaPaSCo, because TaPaSCo will automatically manage data transfers associated with each of the jobs you launch, but for that it needs to know how much data it has to transfer. So we have this make wrap pointer function down here, which takes a pointer to the data you want to transfer and the number of bytes you want to transfer. So that would already be enough to transfer data in and out of the from the FPGA, but in some cases that's inefficient to transport all data in and out after execution, because for example for our grayscaler we want to copy in the 3 channels of our image, but we only want to get out the grayscale image. We don't care about the channels afterwards because they have been compressed to the grayscale image and we don't need that data anymore. We have it in the CPU anyway and it didn't get changed by our grayscale core. So there's 2 functions for that. One is this make in only, which tells TaPaSCo, okay, the wrap pointer I'm giving you created that one with make wrap pointer, copy that data only to the FPGA memory before you start that job, but don't copy it back afterwards. So that's only the in direction, and the exact opposite of that is make out only. So you tell TaPaSCo allocate memory, then your core is going to write its result to that allocated memory, and you only care about that after the execution of your core. So you only want to copy the data out after execution. So that's the 3 functions here. Bit abstract, so let's see an example. Imagine we had a really simple scaling HLS kernel, which just takes an element of an array, multiplies it by 5 and writes it to another array in this case. So we create an instance of the TaPaSCo class. You can we typically call this TaPaSCo, but you can call it any way you want. First thing we need to do is we create a wrap pointer for our input array A. We just take the data of some vector, for example, and tell it the size of that vector. So it was like 100 integers, it would be 400 bytes we want to copy in. And the same we do for B. So for the B array, we still have the pointer to some vector data, and we have the size of that vector it would be the same size as for A in this case. So then it's time to launch our kernel. So you always have, as I said before, in TaPaSCo PEs are always identified by their kernel ID. So you use the ID 42 for the Sobel example, and you use the ID 25 to import your grayscale, and that's the two IDs you need to remember now for the API implementation. You know that your Sobel will have the ID 42, and the grayscale will be 25. So then we say we want to only copy in A, so we wrap it in this make in only, and we only want to copy out B, because in B there's no real data before we start the execution of our core, so we only care about the result, so we make it make out only. So this is going to give us a future in C++ notation, and to wait for the future to complete, we just call it like a function. So if you want to wait for the future in C++, take the name and execute it as a function, so to say. And this is all you need to do to run your HLS kernel that is computing that in hardware. Okay, any questions so far? Last chance to ask. Okay, then it's up to you now. We've already done the first step when we set up TaPaSCo, so you can skip that. If you go to tutorial folder where you've been all the time, there's a software subdirectory, and there's a main TaPaSCo in it. That main TaPaSCo is reading a JPEG image, getting the 3 different channels out of that image, so the RBG channels, and your task now is to run this image to the grayscaler, and after that run it through Sobel to get the edge detection. We've already set up a CMake list for you, so you do not have to do that. You can look at it if you want to see how to work with the CMake targets of TaPaSCo, but it's a pretty basic application CMake. And if you want to run your software afterwards and execute on the FPGA, the grayscaler, and the Sobel, you can use the example image of the so-called Hundertwasserhaus. That's Waldspirale. That's a famous building here, bit north of here, which is built by the famous architect Hundertwasser. So you can, if you generate your output in the /shared directory we set up when we started the Docker container, you will be able to see the images you generate on your own laptop, basically. So if you have any problems, just raise your hand, we will come to you. And now it's time for the funny software part. So I think most of you have accomplished the task of generating a grayscale image and outputting that to the Sobel image afterwards. We'll just run through the solution quickly, or not run, but we'll have a look at the solution. So we have the same skeleton as you have. So I will, just as before, I of course prepared a solution in hours of manual work. So ours is probably a bit different from what you did. We didn't want to have too much of different things in this tutorial today, but I'm going to talk you through all of that. So that's the skeleton you also had up here. Nothing surprising, I guess. So same here, that we use the TaPaSCo class and an instance of that called TaPaSCo. I think your code, it probably looks somewhat similar to that part here. So that's the 3 different channels of the input image. We wrap each of these in a pointer and make it an input only argument to TaPaSCo and save that to different variables. So now comes the part which is probably different in our solution than from what you did, because your solution, probably you copied in the 3 channels of the image, executed a grayscale, got a grayscale image, copied that one out, copied it in for the Sobel, and got the Sobel image out. But in between, we don't really need our grayscale image if we do not want to write that out to a file. So what we did here is we got as a handle. So a handle is basically a pointer to device memory in TaPaSCo. So that's basically filled with an address in the FPGA memory. And then we use the TaPaSCo allocate function here to just allocate a memory of the size width times height. So with this size here, so we're allocating memory with this many bytes on the FPGA memory. So we have this handle gray device up here, and then this is pretty similar to what you did probably. We're launching TaPaSCo with the red input, the green input, and the blue input, and this handle we just allocated. So we have memory allocated for that, and where we want to put our output image. So then we execute our grayscale job here. Probably is very similar to what you did. So we could leave out these two lines if we wanted to, and then we would not get the grayscale image from the device to put it in again for the Sobel, but instead we would just leave it in there and never touch it. So that would be even more efficient because we don't have to copy the grayscale image twice, copy it out and copy it in again. We could leave out these two lines and we wouldn't do that at all. So for the Sobel, it's pretty similar to what you did probably again. We're wrapping that in a pointer, making this output only, launching TaPaSCo with the ID 42, and executing the job and writing the result image. So that should look pretty familiar to you and your solution. Okay, any questions so far when I'm here? Okay, yeah. Then let's build this. Personal opinion, it's good style to not do CMake builds in the same folder. At least that's what I get told all the time, and I think the same. So make a build directory, change to that directory, call CMake. We can look at the CMake file in between if we want to. So that's, we include here the TaPaSCo CMake. So that is all the external CMake definitions of TaPaSCo. We use the find package command of modern CMake to locate the libraries associated with TaPaSCo. We declare an executable called Sobel hardware using these two C++ files. We set the C++ standard 11 as required, and we link our executable with the libTaPaSCo, the libplatform, libJPEG, and libPNG. That's for writing and reading the images. And if you're wondering what the lib dynamic loading does in here, that's only for the simulation tutorial. So you wouldn't need that in a regular TaPaSCo flow, but for sake of the tutorial, you will need that. So we can do a make here. Okay, we've created the executable Sobel hardware here. We can call that one now with the picture of the Hundertwasserhaus. We will put the output images to shared so we can have a look at them. And run that. Okay, let's have a look at the output. So we built a simulator for the sake of this tutorial, but the output of the simulator is was built to like be similar to what TaPaSCo would give you in the debug mode. So you can build the TaPaSCo build libs command we used in the very beginning of this tutorial with an option for the mode debug. So you get a lot of debug output when you run your code. So let's have a look at that a bit. So first thing we do here is we allocate a chop with the ID 42. That's the chop ID, so the number of the chop, and the kernel kind 25, which was the kernel kind we gave for our grayscaler. We're setting the 3 arguments, and the 3 arguments are delayed memory transfers. That's a concept of TaPaSCo, so we will execute the memory transfers associated with that chop only at the point where we execute the chop itself. The 4th argument here, we're setting the handle we allocated before. Then we start to execute our chop 42 in slot 4. That's the slot where our grayscaler processing element is in the hardware, so we execute on slot 4. So what now happens, we now want to execute our chop, so TaPaSCo has to do the delayed or lazy memory transfers now. So he's allocating memory and he's copying over the red channel here, and then writing the pointer to that memory for the first argument, same for the blue and the green channel. Then we're writing the start bit, and then it's executing. Then we get an interrupt at the end, so our core finished successfully. Okay. Then here we are getting back the grayscale image because we wanted to do that to write out the grayscale image. And for the chop 43, which is the execution of our Sobel, it's very similar. We're again setting an argument with a delayed memory transfer, and the memory transfer happens then when it's. So here we're only allocating, because for the Sobel we only want the output image, and after the execution of the Sobel we're getting back the Sobel output image here. And that's all that is basically happening here. So now we can have a look at the images resulting from that. So that's the grayscale picture from our 100 Wasserhaus here in Darmstadt, or Waldspirale as it's called, and that's the edge detected on this image. So if you haven't had an FPGA, you would have actually executed both grayscaling and the Sobel detection in hardware with just these, I don't know, 50 to 100 lines of C++ code as software interface, and the 3 different TaPaSCo commands you use to build the bitstream. So that's all it needs to run TaPaSCo.